This lesson is about antidifferentiation and its properties. At the end of this lesson, you must be able to define antidifferentiation or integration and explain the usage of the properties of indefinite integrals and of the basic integration rules. Okay, let us first define what antiderivatives are, or what is the process of antidifferentiation. A function capital F is called an antiderivative or integral of the function small f on a given interval if capital F prime of x is equal to small f of x for every x in the interval. For example, the function capital F of x defined equal to 1/4 of x to the fourth is an antiderivative of small f of x defined equal to x cubed. Why? Because the derivative of capital F of x, or the derivative with respect to x of 1/4 x to the fourth, is equal to x cubed, which is our small f of x. However, if we take on a function capital G of x defined as 1/4 of x to the fourth plus 10, then this is also an antiderivative of small f, since we can show that the derivative of capital G of x, which is the derivative with respect to x of 1/4 x to the fourth plus 10, is also an x cubed, which is our f of x. So what can be said in general? The antiderivative of a function f of x, which is equal to x cubed, is any function of the form capital F of x is equal to 1/4 x to the fourth plus c, where c is any real number. This is what we call an arbitrary constant. So by the theorem, it states that if capital F of x is any antiderivative of small f of x on an open interval, then for any constant capital C, the function capital F of x plus c is also an antiderivative on that interval. Moreover, each antiderivative of f of x on the interval can be expressed in the form of capital F of x plus c by choosing the constant c appropriately. Let us now define what indefinite integrals are. First, we define the process of finding antiderivatives. This is called antidifferentiation or integration. That is, if the derivative of capital F of x with respect to x is small f of x, then integrating or antidifferentiating the function small f of x produces an antiderivative of the form capital F of x plus c. In general, we denote this by the following symbol. We read this as the integral of f of x dx is capital F of x plus c, where we have the whole thing. The integral of f of x dx is the antiderivative, that this symbol is the integral sign, f of x is the integrand, c is the constant of integration, and dx would indicate that x is the variable of integration. As a whole, this is what we call indefinite integral. Okay, we have here the properties of indefinite integrals and basic integration formula. Okay, these are direct results from getting the antiderivative of the properties of differentiation. So we have this listed as follows. 1. That the integral of dx is equal to x plus c. Recall that when you differentiate x with respect to x, you get a 1. Therefore, the integral of f of x dx would just be the integral of 1 times dx, and that should give you back the variable x plus an arbitrary constant c. This is the definition of an integral. That the integral of a constant c times f of x dx is equal to c times the integral of f of x dx. As a result, this will give us c times capital F of x plus c, where capital F of x is the antiderivative of small f of x. That when you are evaluating the integral of the sum or the difference of n number of functions of f of x, then this is equal to the sum or the difference of the integral of each of these functions. And lastly, the integral of a power of x dx, or the integral of x to the n dx, is given by x to the n plus 1 divided by n plus 1 plus c, provided n is not equal to negative 1. This is called the power formula. Recall that when you are differentiating a power x to the n, remember the derivative would be an n x to the n minus 1. So the exponent decreases by 1. When you work on the integral of x to the n dx, since we are working on the antiderivative, then it is expected that the exponent would be increasing by 1. So we have the integral of x to the n dx will equal x to the n plus 1 over n plus 1 plus c. Again, this is applicable provided n is not equal to negative 1. Let us have now the general power formula. But first, let us recall the chain rule for differentiation. Here it says if y is a function of u and u is a function of x, then the derivative of y with respect to x is given by the derivative of f of u with respect to x, and this will be equal to the derivative of f with respect to u times the derivative of u with respect to x. This is now the basis of what we will have for the general power formula. That in evaluating the integral of f of g of x times g prime of x dx, it will be more convenient to assign g of x as your u and write the differential du representing g prime of x dx. Thus, this integral here can just be written as integral of f of u du, for which the integral would just be equal to capital F of u plus c. Okay, this is a direct result of the definition of the integral. Now, to generalize power formula, we have the integral of f of u to the n times the derivative of f of u to give us f of u to the n plus 1 over n plus 1 plus c, provided n is not equal to negative 1. Or, you may write it in this form. We have the integral of u to the n du equal to u to the n plus 1 divided by n plus 1 plus c, again provided n is not equal to negative 1. So this method that we have used here is sometimes referred to as the method of u substitution, and this may be applied in evaluating an integral with the substitution of u representing g of x and du to represent g prime of x dx. To summarize what we had in this lesson, antidifferentiation or integration is the inverse process of differentiation, and using the basic integration rules facilitates the process of getting the antiderivative of a given differential. That the integral of a power whose base is a function of x can be evaluated by using, but not limited to, the general power formula for integration.